9, 8.
I'm Matt Balhoff. I'm a petroleum engineering faculty member at the University of Texas at Austin. This is a video lecture on solving the heat equation for flow-through porous media using the explicit and the implicit method. And we'll do it two ways. We'll start out by doing it in Microsoft Excel. It's a nice little small toy example, and it's a good way to help us understand how the problem is solved. We will also do it in Matlab. The Excel method is nice for visualization, but it's not very flexible. We'll write a code in Matlab which allows us to change the number of grid sizes, etc., much more flexible. So just to recall, the heat equation is a parabolic second-order PDE. It's given by this equation. This comes into focus. Okay, so this is that, and then what we need is two boundary conditions. So we need a boundary condition at x is equal to 0 and x is equal to L. That could be a constant pressure condition, so for example 2000 psi, or it could be a no-flow boundary condition or a flux boundary condition. Okay, it doesn't have to be no flow, but that's usually what we do. It could be a constant flow. And on the other side, again, we could have a Dirichlet, a constant pressure condition, or a flow boundary condition. In this case, we'll do a flow, for example, and say dp dx is equal to 0. And since flux is proportional to pressure gradient, dp dx is equal to 0 is the same thing as saying q is equal to 0. We'd also need an initial condition. In our initial condition, it says that time is equal to 0, p is equal to a constant maybe, so 1000 psi. Okay, or it could be something where you said p is a varying of x, but you have an initial condition. What is the initial value? So that's the kind of problem we want to do, and we're going to solve it by using the explicit method. Okay, and the formula for that is p of I n plus 1 is equal to p of I of n plus eta times p of I minus n to the n minus 2 pi eta to 2 pi to the n, pi plus 1 to the n. And then there's the implicit method, where we actually solve a system of equations. In the implicit method, what we do is we've got a matrix. So you do this for I is equal to 1 to n, and you can do the same thing over here, where we say that minus eta pi to the n plus 1 plus 1 plus 2 eta pi to the n plus 1 minus eta pi plus 1 to the n plus 1 is equal to pi to the n, right? That's the implicit method. In this case, you can solve each equation independently because it's explicit. In this case, when you solve it for I is equal to 1 to n, you get a system of equations that you have to solve. So you have to solve something like ax is equal to b, and you've got to solve that linear system of equations. But let's go to Microsoft Excel. And you should follow along with this problem. So you should get a copy of this blank file and follow along and do as I do. So again, if you fall behind, pause the video and try to catch up, or rewind the video, or start all over again if you need to. But take it as slow as you need to follow along. If you don't follow along, I don't think that you'll really understand what's going on. So here's my spreadsheet, and what I did is up in the blue is all of my conditions, all my inputs. So I've got reservoir properties. For example, it's 1,000 foot long, and it's porosity is 20%, and the permeability is 50 millidarcies. Thickness is 10 feet, width is 100 feet, that kind of stuff. We're going to have fluid properties, a viscosity of 1 centipoise, a compressibility of 1 times 10 to the minus 6 inverse psi, a formation volume factor of 1 reservoir barrel per stock tank barrel. These are all things I could change. The boundary conditions, I'm going to say that it's 2,000 psi, and by using the number 1, that tells me it's a Dirichlet condition. If I had to 0, that would be a flux condition, but I'm going to do 1 there. And in this case, I use a Neumann boundary condition at x is equal to L, and that's a no flow, so it's a 0. And the initial condition is 1,000 psi everywhere. So at t is equal to 0, the pressure is equal to 1,000 psi. So again, this is the explicit method, and what we have is we want to solve for the pressure in every grid block with time. So what we've got is it's on 11 grid blocks, n is equal to 11. Okay, delta x is going to be the length of the reservoir, which is 1,000 feet divided by 11. So that was B2 divided by B10. That was 90.9 feet. Alpha is the diffusivity constant. Diffusivity constant is the permeability K divided by the viscosity mu divided by the porosity phi divided by the compressibility CT. So these were all things in there, and we get 2.5 times 10 to the 8th millidarcy psi per centipoise. And then we use a dimensionless variable, which is eta, which is the diffusivity constant alpha times delta t, the time step, that's 0.002 days, divided by the grid block size delta x squared. Okay, and we do have to multiply by a conversion constant, which is 6.33 times 10 to the minus 3, and so that's what we get up there. So eta in this case is 0.383. And what again I want to do is I want to solve for the pressure in every grid block. There's 11 grid blocks, n is equal to 11, at different times. So I'm going to start at my first time step, my second time step, etc. Stuff like that. Now my initial condition was 1,000 psi, so I could just do, see, it's 1,000 all across over there. Okay, and I set up this little spreadsheet, and again, each time step is 0.002 days, so I just added 0.002 days for every row. And I'm going to make like a little, I'm going to make columns and rows and put in each of those. I'm going to try to solve for the pressure at each time step. Maybe this shouldn't have been 0, maybe this should have been 1 actually, but it doesn't really matter. So this is or maybe even 2, because this is the first time step. So it doesn't really matter that much. We're going to try to solve for the times. But the point is our initial condition is, on this should have been 0. Okay, so the initial condition was 1,000 psi, right? We know that. And we're going to use our formula up here to solve for the pressure in every grid block in the next time step. So if we go to the next time, actually, no, I'm sorry, this probably would have been 1. So that's 1, not a big deal, but the pressure in a grid block is going to be equal to the pressure in the previous time step. That's going to be D18. It was previously 1,000 psi in that grid block, plus alpha delta t over delta x squared. That's eta. So that's going to be B13, and I'm going to use that eta over and over again, so I want to use the $B $13 sign. So I'm going to, you could actually go through and you could put in $B $13. If you're not familiar with the dollar command, what that does is it freezes it, so when you use it in different rows or columns, it always uses B13, and it doesn't use B14 or B15 or C13 or D13 or your E13, stuff like that. So it's D18 plus $B $13. There's another way I can do that. I can put B13 and I can press F4 on my keyboard, and well, it should work. It doesn't work on this keyboard. Well, that's okay. But on most keyboards it works. So I guess I'm going to have to do it manually, but I bet on yours it'll work if you do F4. So it's $B $13 times, let's look at our formula, pi minus 1 minus 2 pi plus pi plus 1. So it's going to be times the pressure at the last time step, but at the grid block to the left. So it's going to be C18 minus 2 times pi to the n. So it's the pressure at the previous time step in that grid block. So it's D18 plus pressure in the grid block to the right, that's E18. And notice I do not use the dollar sign at all on those. It was only on B13, the eta. And I get my new pressure, and it looks like my pressure hasn't changed in that grid block at all. And that's actually right. Now what I can do is I can drag this across for all the other grid blocks, and you can see grid blocks 2 through 10, their pressures didn't change at all. Okay? And that's actually correct. Okay, but don't just type in 1,000. That won't be right, because they're going to change later, and you want to put in the formula. Okay, so this is what we get. So there's 1,000. Now, what do we do at the edges, at the boundaries? Well, we got boundary conditions, right? So the problem is if I use this formula, and you can see the formula by dragging it goes across. So in this case, when I was at H19, I was using that, and what I did was I was using this pressure, I was using that pressure, G18, and I was using I18. So I was using all these pressures right there to change that pressure. And likewise over here, I was using these three pressures to do that one. Well, this is difficult because I want to use this pressure, that pressure, and wait a minute, that's not a pressure at all over there. That's nothing. So I got to use my boundary conditions. And in this case, I've got a Dirichlet boundary condition. So let's go back to the dot cam. And recall my formula for the explicit method looks like pi to the n plus 1 equal to pi to the n plus eta pi minus 1. Okay, I'm going to write that equation for every grid block, but if I'm at the edge, and if I is equal to 1, then I plus 1 is equal to 2, then I minus 1 would be 0, and that doesn't make any sense, right? P0 is equal to, well, that doesn't make any sense. There is no P0. There's no zero grid block, but we learned about boundary conditions in class. And what we learned is if it's a Dirichlet boundary condition, that P0 would be equal to TP boundary minus P1. Otherwise, P0 is equal to P1, right? We had my grid blocks. This is block number 1, 2, 3, 4, etc. This is an imaginary block P0. Okay, if it was a Neumann condition, so if it's otherwise it's a Neumann, no flow, we say P naught is equal to P1. So what I can do is I can just plug that into the formula right there. So wherever I had a PMI minus 1 to the n, I would put 2BB minus P1, and P naught is equal to P1. So what I want to do is I'm going to use an if statement. Let me go back to over here. And, well, you know what? I'm going to drag it over anyway, even though I know it's wrong. I'm going to drag this over there, and I get 616.04. Well, that's not correct. And the problem, of course, is if I go into my formula at the top, and let me do something real quick. I'm going to increase my font so you can see a little bit better. But here, my formula used C18, D18, and it used B18, and B18 is a meaningless cell. Okay, that's the time. I don't want to use it. So this was obviously wrong. Okay, that's not what I wanted to use. What I really wanted to do is if it's a Dirichlet boundary condition, I wanted to say it's 2 times the boundary pressure minus P1. Okay, and if statements work a lot like they did in Matlab or any programming language. I can say if the boundary condition, which is this cell right there, that's F10. If F10 is equal to 1, that means it's a Dirichlet boundary condition, in which case that first cell, that Pi minus 1, will be 2 times my boundary pressure, which was 2,000 psi, or I should say 2 times F9. Okay, minus P1, where P1 was going to be the C18 value, right? Now, if it's not, okay, and then I put comma, I've said if it's not a Dirichlet boundary condition, it's a Neumann boundary condition, in which case Pi minus 1 would just be equal to P1. So P0 is equal to P1, in which case I would just say it's equal to C18. I think that that's going to work. Okay, and there we go. Now I get a pressure of 1765.93 in block number 1, and that actually makes a lot of sense, doesn't it? Because the boundary pressure was 2,000 psi, and the center of block 1 isn't quite at there. In fact, here it is. It's at 45.45 feet. So at 0 feet, we know that the pressure is 2,000 psi. All right, it's 1,000 everywhere else. And so we think it's going to be close to 2,000, but not quite, 1765. I think that makes sense. Okay, now let me just show you. Over here. You should have been able to see it on the screen when I did it. But this was the formula I used on the left. Oh, you know what? I may have forgotten to use my dollar sign, so maybe you should go back and do that. All right? So I said if F10, okay, that's if that Dirichlet, if the boundary condition is 1, meaning if it's a Dirichlet condition, then it's 2 times the boundary pressure, $F$9, minus P1, which is C18. If not, if it was not 1, then it must have been a Neumann boundary condition, in which case P0 is equal to P1, which is C18. And then, of course, it's minus 2 times P1 plus P2. So going back over here, and I may have made a mistake originally, or not a mistake, but maybe I forgot to put my dollar signs, and I did. So if F10, so again, you should be able to use your F4 command, but if not, you can just use the dollar sign. So if $F10 is equal to 1, then it's 2 times $F$9. And that dollar sign is very important, because even though it worked right there, remember we're going to drag and drop, and we're going to go from there. So that's 1765. Now what about at block number 11 in this cell? Well, again, I'm going to drag again, and again I get 617, which is not right. Okay, that's incorrect. And the reason is because it looks like it's using N18. It's using this cell right here, which is meaningless. So that's not what we want to use for the block at the edge, the Pn plus 1. We want to do something similar. We want to say if, open parentheses, this, that's the outlet boundary condition, if that's equal to 1, if that were a Dirichlet boundary condition, then we would say that that's going to be 2 times whatever this pressure is, okay, F11, minus Pn. So that's going to be that pressure right there, M18. Okay? Now, if it's not 1, in this case it looks like it's 0, so it actually isn't 1, then what I do is it means it's a Neumann boundary condition, meaning that Pn plus 1 is equal to Pn. So I would just use M18 actually. And let me make sure I got my dollar signs all, well, I'm going to close this first. But I need to, again, I need to use dollar signs here. So I'm going to do that. $F, $12. And I'm going to use $F, $11. So please don't just be typing this out blindly. Make sure you understand why I'm doing that. And if you don't, maybe you need to rewind the video and watch what I was doing and my explanation again, or maybe you need to go back and look at the PowerPoint notes as an explanation of how boundary conditions work. But if you're just typing this out as I'm doing and not understanding what I'm doing, then when it goes to the homework and I give you a slightly different problem, then you're going to mess it up then, even if you get it right here. So there we go. So it wasn't equal to 1. It's not a Dirichlet boundary condition. It's a Neumann boundary condition. So dp dx is equal to 0. That was a boundary condition there. This is the pressure. Right, this is all at time is equal to 1. So the pressure is 1765. It goes to 0. Now, if I want to solve it for other time steps, the really neat thing about Excel is you've got the drag and drop option. So I'm going to highlight all these cells. I just highlighted them all. You can drag down like this if you want. See if that works. It does. Or I'm going to do something easier. I'm going to highlight it all. I'm going to go to the bottom right corner, and you can see where this white cross, kind of if I go to the bottom right, it turns into a thinner black cross. I'm going to double left click it, and look at that. It's going to form all those pressures. And you can see what's happening is the pressures are increasing as a result of the boundary condition on the left, and they're going up, throughout, and eventually it comes to steady state if I go to long enough. Eventually it's going to be, look, it's going to be 2,000 psi everywhere, and that's actually what we expect it to do. Now, that's my solution there. Let's go look at the plot. So I actually made a plot for you. Okay, I didn't make the plot until you actually did the solution. But recall that this is a plot of pressure versus distance along the reservoir at different times. So recall that the initial condition was 0. So what it's doing, this blue plot at the very bottom, is just plotting pressures here, so 1,000 psi. So that's the initial condition. And then what we're doing is we're plotting the grid block pressures at different times as time goes on. So the boundary condition is P is equal to 2,000. And over on the right, it was a no flux boundary condition. No flux means that dp dx, the gradient of pressure, is equal to 0. So that means the slope at x is equal to L should equal to 0. And look at that. Look at the plot. Okay? Look at the plot. You can see that dp dx is flattening out as it gets to the edge. Right? And over here, pressure is equal to 2,000. Now, if I had used more grid blocks, that would have been maybe more clear. Okay? One of the things I love to ask on tests, okay, and you can bet on this, that this will be on the test, I will ask you to make qualitative plots of what the pressure should look like at different times along the reservoir given different boundary and initial conditions. Okay, and you should be able to draw what this should be on your own without actually having to solve the problem, just qualitatively. You can bet that that will be on the midterm and or final exam. Okay, that's under those boundary conditions, so that's what we get. This is the pressure, this is versus distance, this is at early times, this is a little bit later times as time goes on. Eventually, what would happen is it would go to even later times, right? And so this eventually would be flat. Okay, I'm going to change some things up. What happens if I said, wait a minute, what if I made my boundary condition on the left Neumann, and on the right, I'll make it a Dirichlet boundary condition. So on the right, it's 2,000 psi, but on the left, it's only, so I made this 0 by Neumann, and it doesn't really matter what I put there. I can put 0, but that tells us it's going to be no flux. This is going to be it's a constant pressure of 2,000. Let's go look and see what happens to the pressure. Look, it changed. Okay, so now it's no flux, so the gradient dp dx at x is equal to 0 is 0, and then over here at x is equal to L, it's going up to the boundary condition, and right at the edge it would be equal to 2,000 psi. All right, let's do another thing. What happens if we use two Dirichlet boundary conditions? I could say it's 2,000 at x is equal to L and 1,000 at x is equal to 1. All right, well that changes the whole solution. You can look and you can see that the numbers have all changed. And if I go to my plot, look what's happening. So in the initial condition was still 1,000, but at all other times, the pressure was 2,000 there, and it was 1,000 over here, and you could see that it's something different in between. And as you get to steady state, you go to late times, eventually you get a straight line going from 2,000 to 1,000. But at earlier times, it's actually kind of, and it would have been nice to actually plot more times, because at very early times, it would have gone kind of almost immediately down and then done this flat. Okay, and then it would have slowly started to come more, and eventually at steady state, you just get a straight flat line. So that's the solution. I could go back and do what I had originally, which is this is being a Neumann condition, changes all those numbers in here, I get an explicit. That was what I had originally. Now, I could change the time step, and I would get a little bit different answer. Okay, I could. All right, so it changes it up a little bit, but you should be qualitatively still getting the same results. Now, what if I wanted to use bigger time steps so I go to further times or do less calculations, something like that? Well, why don't I do this? Why don't I use a step size of 0.00265 days? Okay. Well, before I do that, what did I have? I had 0.002 originally. My eta was 0.383, right? If I go to 0.00265, eta is 0.507. And if I recall correctly, in the explicit method, in order for the explicit method to be stable, what happens is that eta has to be below 0.5. And now eta is 0.507. because eta was alpha times delta t over delta x squared. So by making delta t bigger, I actually made eta bigger, and in this case it went above 0.5. So if I go to my explicit plot, what do I get? Whoa, something weird happened here. This is unstable. Okay, I'm getting unrealistic answers. The errors are propagating. So by using this time step, eta is over 0.5, and you can even go look. If I go to late enough times, I bet look, it just goes haywire. Okay, I get just, I just get a mess for my answer. Okay, so I cannot use a time step which gives an eta greater than 0.0265. I got to use something smaller. Okay, I could do that and it would have been fine. Yeah, I could have used 0.0. I could use something smaller if I wanted. That would have been fine too. Okay, and here's what I get. All right, so that's the explicit method. And if you didn't understand all that, maybe start from the beginning and redo it again, or go do a hand problem on your own, or go back and look at the PowerPoint videos or something. But you should understand how to do all this, and for a homework problem, you'll probably be given something similar, but maybe with a different number of grid blocks, and start all over again or something. So with that, let's pause the video. Okay, so that completes the explicit method. We're going to move on to the implicit method now, and the implicit's more difficult. So if you didn't understand the explicit method, then I don't think you'll understand the implicit. So maybe rewatch the video if you need to, or if not, if you understood everything, let's move on to the implicit method. You should be following along and doing this on your own. That's the only way to learn this. So make sure that you are following along and doing exactly the same thing and exactly the same answers. Otherwise, watching this video isn't all that helpful. So let's go to the implicit method. So I'm clicking on the tab that says implicit now. And this is implicit. What we have is what we have in blue is really exactly the same thing we had before, right? Because we're solving the same reservoir, the same fluid properties, the same number of grid blocks, and the same boundary conditions, everything. We're just going to solve it using the implicit instead of the explicit method. And the equation for every block is given here by this equation. It's implicit because everything on the left is unknown. The pressures on the left are unknown. The coefficients are constant. Those are known. And we know the right-hand side. We know pi to the n. All right? So what we really want to do is we need to set up a system of equations and solve it. So let me go back over to the .cam. And we want to solve a system of equations, kind of like AX is equal to B, right? Where X is our pressures, our new pressures we want to solve for. And A, our matrix, is a square matrix. We have 11 grid blocks, so it'll be an 11 by 11 system of equations, which looks like, well, it's going to be usually, something like, minus eta, and so on the main diagonal we'll have 2 times eta plus 1. Remember, eta was our dimensionless constant, where eta was alpha times delta t over delta x squared, and we might have had to multiply it by a conversion constant and get it in the right units. This is dimensionless, right? The main diagonal gives 2 eta plus 1 in general, and then right of the main diagonal is minus eta, left of the main diagonal is minus eta. Okay, now I will say that the coefficients here depend on the boundary condition. Okay, and it turns out if it's a Dirichlet boundary condition, this would be a 3. If it's Neumann, it'd be a 1. It won't be 2 like the main diagonal. Same thing over here. If you had a Dirichlet at x is equal to L, this would be a 3 for Dirichlet. And you can work out the math to prove yourself that. We've done it before in class. 1 for Neumann. Okay, so that's what my A matrix looks like. And then my B vector is actually going to be, my old P's. Okay. Oh, let me do that down here. It's going to be my old pressures. But if you got a boundary condition, if you have a Dirichlet boundary condition, then it'll actually be 2pb eta. This would be for Dirichlet. It's equal to 0 for Neumann. And then again, go back and look at what we did in class with the notes. You should understand how to do those. But basically the idea is if we want to solve for the system of equations, we want to solve AX is equal to B, where A is my square matrix, B is my right-hand side vector with the old pressures and boundaries, and I solve Pn. Well, the easiest way to do it, well, in Excel, one way to do it is to take the inverse of A, multiply it by B, and that gives you the pressure, and that's what we'll do. So our steps, what we're going to do is we're going to form the matrix. It's going to be an 11 by 11 matrix. We're going to invert the matrix. So I'll give you like A inverse. Then we're going to, what will we do? We'll form B. Form B. And then we'll solve A inverse B. And then we will repeat for all time steps. Okay, those are our 5 steps. So the first thing we want to do is form the matrix. The matrix looks like this. It's tridiagonal. So let's go back to Excel and do that. So I was on this tab that said Explicit. I'm going to go to the tab that says Implicit Matrix. And I already made it nice and easy for you. I made a little 11 by 11 matrix. I just filled it in with all zeros. I was trying to save time for me and you. It's all zeros, but let's do the hard part together. We've got to fill in what this, what these are. So remember, on the main diagonal, what we had is 1 plus 2 eta, or 2 eta plus 1, whatever. But it's equal to 1 plus 2 times eta. Eta was that dimensionless constant. What was that? Let's go click on the implicit tab and click on B13. Okay, and I'm going to go, so do that. And so that's what that is. But let's be careful. We're going to use that over and over again. So I'm going to do $B, $13, and that's that. And all the main diagonals are going to be 1 plus 2 eta. So I'm going to do Control C, Control V, Control V. I'm going to put it all in the main diagonal. Now, in the first and last row, right, the corners are going to be a little bit different. But you know what? I'm going to put them there for now. I'll fix it later. Okay, I know that this isn't going to be right, but at A11 and ANN, it's not quite right, but that's okay. So that's that. And then on the off diagonals, it's a tridiagonal matrix, I'm going to have minus eta. So it's going to be equal to minus, keyboard error there. Can you pause the video?
Sure, 1 second.
Okay, we're back. I had a keyboard malfunction, but everything seems to be fine now. Let's go back to the screen, and we had already done the main diagonals. So all the diagonals are in there. We know that this one, A11 and A1111, are going to be, they're not right. We'll fix those later. But let's do the off diagonals. They're going to be minus eta. So right here, we're going to do equal to negative. Let's go to the implicit tab. Let's click on B13, and I'll do that. Okay, so that's minus 0.38, and I'll put the dollar sign, in there because I'm going to use it again. And so I'm going to do Control C. I'm going to make my life easier and just do Control V everywhere. Put it. I mean, you could type in the value, or you can type in the equation everywhere, but I'm going to make sure it's tridiagonal. Okay, don't put it in the wrong place, then you're going to get a wrong answer. Okay, so I just used Control V everywhere, and I went through, and I think that that's right. Okay, this looks tridiagonal. I got 1.766 on the main diagonal, minus 0.383 to the right of the main diagonal, and minus 0.383 to the left of the main diagonal. That's my minus eta. Oh, I missed one. I missed one right there. So let's do Control C, Control V. Okay, so now it looks right to me. I think it's right. So this is that. We got one more thing to do. We need to put our boundary conditions in for A and N and A11. Okay, and I want to make it flexible. I want to be able to change my boundary conditions to Dirichlet and Neumann and switch it. I want my code to work no matter what, because next week I might come and want to do a different problem with different boundary conditions. So that's why I'm going to do the if statement. So here is what matters, is that, and we already did that. We derived it, and we found that, look, this coefficient, which I have nominally is 2, so it's 1 plus 2 times eta, should actually be a 3 if it's a Dirichlet boundary condition. It should be a 1 if it's a Neumann boundary condition. So let's delete that 2, and I'm going to put an if statement. If, and let's go back to my implicit tab, if F10 is equal to 1, comma. Okay, so, and if this is equal to 1, then that means, and you see I even put it in parentheses there, 1 means Dirichlet. So it's if a Dirichlet, then I want the coefficient to be a 3. So I'm going to put the comma, I'm going to put 3, and if it's not 1, then comma, I want it to be a 1. So it's actually never 2. Okay, I'm going to close my parentheses, I'm going to do that, and I get that. And you can see that it was a Dirichlet boundary condition, so it's 1 plus 3 eta. And 1 plus 3 eta is 2.149. You can double check that. We can even do it here. So equal to 1 plus 3 times eta was 0.383, 2.149, so it did that right. We want to do something similar over here. So let's do another if statement. So get rid of that 2, plus if, open parentheses, go to the implicit tab. Now it's this one, it's the outlet boundary condition. So if F12 is equal to 1, then this is our boundary condition. Otherwise, let's make it, oh no, if F12 is equal to 1, we want that to be a 3. Otherwise, we want it to be a 1. Just close parentheses, do that, and we get 1.383. And again, we can test that. So it's equal to 1 plus 1 times eta, 0.383. So that's right. So it's at least right for the boundary condition. That's what our matrix looks like. We can switch things around. Let's go over here and let's make this 0 and make that a 1. So that would mean that we've got a Dirichlet on the right, but a Neumann on the left. And if I go look at my implicit, now this became a 2.149, this one became a 1.383. Okay, what if I made them both Dirichlet boundary conditions? Well, you get a 2.149 and a 2.149. Perfect. Okay, so my if statement's working well. Let's go back to what we had before, which is Dirichlet on the left, Neumann on the right. Okay, this is what my matrix looks like. It's tridiagonal, as we expected. What do we want to do now? That was step 1, right over there, is to form the matrix. So step 1 we got right. Step number 2 is to invert the matrix. Okay, so we want to take the inverse of the matrix. We can do that in Matlab. I mean, in Excel, excuse me. It's a little tricky. It's a little tricky. And so you need to really, really, really pay attention now, because I guarantee you that most people are going to miss this when I do it the first time. So pay attention, and even when you pay attention, you'll probably get it wrong. So when you get it wrong, rewind the video, watch it again. And if you get it wrong again, then rewind the video and watch it again and keep on doing it until you get it right, okay? Don't get frustrated. It's just a little tricky, all right? So what we want to do is we want to invert this matrix. And in fact, I wouldn't be surprised if I didn't get it right the first time because it's that tricky. We want to take the inverse of this whole matrix. So what we're going to do, and we want to put it right here. So the first thing is, and this is where a lot of people will make a mistake, is you need to highlight that entire region where you want to put it. So from B21 all the way to L31, that needs to be highlighted. And then I'll go up to the screen up here. You see where I'm at right over here, up to the little equation line. And I'm going to put equal to, and we're going to use the M inverse command. Make sure I spell it right, which I did not. M inverse. So that means to take the inverse of a matrix. What matrix do we want to take? We want to highlight the whole region, and I'm going to close it, but don't press the enter button yet. Do not press the enter button yet. Instead of what we want to do is I want to press Control Shift Enter all at the same time. Control Shift Enter. Okay, and this is on a PC. Okay, if you have a Mac, I don't really know what the command is, or something similar. Google it. Look on the Excel's help. Okay, I know there's something similar on a Mac. I'm not a Mac guy, but on a PC, that's how you do it. Control Shift Enter, and this is what the inverse of the matrix looks like. So check to see you got the same thing I did. Okay, your matrix originally better have been the same. If you had any differences there, then you definitely won't get the right answer. If you did have the right matrix as me, but didn't get the matrix inverse correctly, maybe you didn't follow the steps right. So I'm going to do it one more time, okay, but you can listen to me as many times as you want by rewinding the video and watching it. So I'm going to delete it, and I'm going to show you what I did again. So what I did is I highlighted the whole region, okay. We're going to go up to this equation screen up there. I'm going to say equal to M inverse. This is on a PC again. You're going to highlight the matrix we want to invert. So that's B6 to 1116. I'm going to close parentheses. I'm not going to press enter yet. Instead, I'm going to press Control Shift Enter, and I get my matrix. And I am fairly certain that that's the right value. I'm going to double check my notes, and that's the right answer. So this is the inverse of our matrix. If you haven't gotten this, if you're not getting this, then stop the video and keep on trying until you get it. If you're using a Mac, then there's a simple command to do it as well. You might just need to use Excel's help or Google it or something like that. So back to the .cam. This is, we inverted the matrix. Now the next step is to form B. B is simply the pressures of the last time step plus a boundary condition if it's Dirichlet. It's actually, these are all adding zeros when you don't have a boundary. And if you have a Dirichlet boundary condition, a Neumann boundary condition, it's also 0. So really, it's only if we have a Dirichlet boundary condition that we have to do something. Let's go over here. And that's what this is over here. This is the B vector, okay? But I made it a row vector, not a column vector. And you can see what this is. I actually did the hard work for you. So I actually put that in. You can see I've got an if statement in there for the boundary condition. It's right over there. And this is going to be 1,000 because 1,000 is the initial pressure. Plus on block number 1 there was a Dirichlet boundary condition, so it's 2531. Again, if I could have done 1 and 1 and maybe, if we had done, then that changes it over there. You could have done 0 here, and change it, and this would have changed. So we'll do 1 like we had it and 0 like we had it before. And I should say that I think when I did this, I made it really general. I didn't just do a no flux boundary condition. I made it to where it would work for a flux boundary condition, so a constant rate. But let's not worry about that. Let's just we got a no flux boundary condition, let's say 0 cubic feet per day, and then tell it 0 for Neumann. Okay, so this is the right-hand vector. So this is my B vector, but it is a row vector, so we should note that. So going back to the dot cam, we did part 3. So we've formed the matrix A, we inverted the matrix, we formed B, we've got those 3, and that's a row vector. And then we want to solve for our new pressures in the next time step, which is A inverse B. All right, now recall that when we normally do this, P is going to be A inverse, and that's a square matrix. So this is A inverse. This is B, which is a column vector. Okay, and then this would give us P new, Pn plus 1, which is a row vector. Okay, there's a couple of tricky things. We're going to use the mmult command. We're going to use the mmult command, which is matrix multiplication. So that's going to allow us to multiply this matrix A inverse, which we created, times our B vector, and give us our new pressure. There's a couple tricky aspects here, though. There's a couple tricky aspects. The first one is that B is supposed to be a column vector, but it's not. It's a row vector in Excel. So I have to transpose it. So I'm going to have to use a transpose command. So I'm going to have to matrix multiply A inverse times not B, but the transpose of B, because B was a row vector, and I'll get my pressure, which will be a column vector like it's supposed to, but then in Excel, the way I've got the program set up, I want P to be a row vector as well, so I'm going to transpose that. So I'm going to have to take the transpose of, and do matrix multiplication, mmult, of A inverse times the transpose of B, and so it's going to get a little ugly when I type in the formula. And the formula, if I've got it, looks like what I've got down there at the bottom. Okay, so what I'm going to do, I want to do matrix multiplication of that matrix. And I'm going to multiply this matrix by the transpose of that vector B, and I'm going to do the matrix multiplication there. And then when I get the answer, it'll be a column vector, so I actually want to transpose that. The other tricky things I got to note is that I want dollar signs there, because the matrix is never going to change. It's always going to be those same, but there's no dollar signs over there. So there's a lot of tricky things here. You can use that. Then the last tricky thing is, remember that we had to do that whole highlighting the region and doing Control Shift Enter. So it can be very easy to make some mistakes here. If you made mistakes before, or even if you didn't, you're definitely likely to make some mistakes here. So it might take you a couple tries to get this right. Sometimes it takes me a couple tries to get it right. But here's what we want. Oh, you know what? I did it for you. Yeah, oh, I cheated. So I'm going to delete it, though, and I'm going to do it again. Okay, so this was the initial pressure, and I'm going to highlight this region, because that's where I want to put the answer. Remember, we highlight the answer where we put it. And I'm going to say equal to transpose of matrix inverse, not the matrix, but the matrix inverse. So this whole region. You know what? I already made a mistake, so let me back up. I got to delete it. It's not going to be. It's going to be the transpose of matrix multiplication. So transpose of matrix multiplication, open parentheses. Now I highlight this. Matrix multiply that with the transpose. I'm going to delete that. I want transpose of my B vector. My B vector is this. Close, close, close. Make sure I got the right number of parentheses. And then I'm going to put dollar signs around B21 and L31. I don't put dollar signs around this because my B vector will change in every time step, but my A matrix, A inverse, will never change. So I think I got the equation right now. All right, I'm matrix multiplying my matrix inverse times the transpose of that right-hand side vector. I get an answer, and then I transpose it. I'm not going to press the enter button yet. Instead, I'm going to press Control-Shift-Enter, and I'm going to cross my fingers. And, well, I think it worked. Okay. So this is what I get. I'm going to double check my results, and I'm pretty sure that's right. So 1371, 1084, 1019, this is my pressures. If you didn't get that, I'm not surprised. There's a lot of places you could have made a mistake in that calculation, so just redo it until you get it. It's a little frustrating, but if you got it, then now things are easy. So these are the pressures, and they make sense, right? So the boundary condition on the left was 2,000 psi. So I expected my pressure to rise on the left, and it did. It went from 1,000 to 1371, and it increased some other places, but just not as much. And then on the right, we've got that Neumann boundary condition, so dp dx is equal to 0. And it hasn't felt the effects of that boundary condition yet. I'm going to go over here, and now I'm going to update my B vector. So what I'm going to do is I'm going to highlight all this. I'm going to drag and drop. So my B vector has changed a little bit because it actually should be equal to my old pressures, which it is, plus the boundary condition. And now what I'm going to do is, if you did everything right, and if you did the dollar signs correctly, then all I got to do now is highlight both my pressures in my right-hand side, and I'm going to go over here. I'm going to make my little black cross, and I'm going to double left click with my mouse. And it's going to compute the pressures at all time steps. You can see the pressure is increasing everywhere. If I go to late enough times, then it comes to equilibrium. I probably should have gone to more time steps, but it's getting right to about 2,000 psi. And if I go look at my implicit plot, so this tab down here, I look at my pressures, and look what we got. This is pressure versus distance. It looks a lot like the explicit solution, and it should. I mean, they're just two different methods for solving the same problem. I should get the same answer or close to it, and I do, right? So over here we had our boundary condition of 2,000 psi at x is equal to 0, and so as you get, we've only got 11 grid blocks, so we don't get all the way to 2,000 psi, but we get close. We got a no flux boundary condition over here, and so that works pretty good. One other thing I want to show you is that, remember, with the explicit method, if I chose too big of a time step, so if I chose 0.00265, then eta went above 0.5, and then it became unstable. It was a mess. Implicit, no problem. Okay, if I could have chosen 0.004, no problem, right? So implicit method is unconditionally stable, right? So I can go by, I can use whatever. Other thing is I can show you different boundary conditions. Let's do Dirichlet on both sides. Okay, expected results. This is similar to what we saw with the explicit. I can, and this is because that was what was nice about using those if statements, is now I can do whatever I want here. I can keep this as that. I can make these no flow boundary conditions. Cool, right? All that makes sense. Now I got a no flow or a zero gradient there, and this is going out to my boundary condition of 2,000 psi. So that completes the Excel portion of. This is just a simple way of solving the heat equation using Excel. Okay, we were kind of restricted to a small number of grid blocks. If I wanted to do 1,000 grid blocks now, that would be a real pain, wouldn't it? I mean, I'd have to add more columns, and it would just be a mess. Okay, it was easy to change the time step, but I couldn't change the number of grid blocks or anything. And things would get really slow. So the next thing we're going to do is we're going to redo the problem, but we're going to do it in Matlab. We're going to write a code to solve the problem using the explicit method. So we're going to stop this code. And what I'm going to do in So we want to do that whole problem again, but we want to do it in Matlab. And the right way to program, and this is important, the right way to program is first off to do some things with a pencil and paper and think about what you want to do the problem by hand, to kind of scratch some things out. That's really the only way to program, and to really think about what you're doing, and also to break it up into parts. So if you try to do everything at once, then it can get really intimidating. And I mean, I've been programming for forever. I've been programming for 15 years now, and I can't do it. If I try to do everything at once, and I try to program with just the computer screen up, and I mean, I'm going to get it wrong every time. Okay, but if I do things with a pencil and a paper, and if I break it up into parts and it becomes manageable, then I can do it, and it's not a big problem if I think about it. So let's do the problem together, and you know what? We're going to use the same steps that we solved the problem in Excel. So we're going to go back to the explicit problem. So the equation for that was it looked like this, okay? And we had to solve that equation for every grid block, I is equal to 1, I is equal to 2, I is equal to 3, all the way to I is equal to capital N. And then when we did that, we would have to move on to the next time step, right? And then do it, while the time was less than some maximum time I told it. So you do that until the time is equal to the time max. So we need some things in here. This is the problem we want to solve, but we need to know eta. Eta is alpha delta t delta x squared. So we need to define our time step and our delta x. Okay, to know our delta x, I need to know what n is, because delta x is the length of the reservoir divided by n. So n is the number of grid blocks. I'll need to know L, the length of the reservoir. I'll also need to know alpha. Alpha is equal to K over phi mu CT. So I need to know what the viscosity, the porosity, the compressibility, the permeability, the reservoir length, the number of grid blocks I want to use N, the time step delta T, and then I want to calculate delta X. And then I need some other things. I need some boundary conditions, right? So this problem has boundary conditions. And it's got initial conditions, right? So maybe we said, pressure is equal to 2,000 on the left at x is equal to 0, and dP dx is equal to 0 at x is equal to L. And then we define some initial conditions like P is equal to 1,000 initially. So let's do all that. So let's write my code. And the first thing I got to do is kind of, remember the Excel problem we did where we had that blue box at the top of the Excel spreadsheet? We want to do the equivalent of the blue box in Matlab, which is just to initialize all the stuff we know, like reservoir properties and boundary conditions. So if we were writing a script file, we would have to define all those properties. So what you should do is actually right now, with a pencil and a paper, write all this down. So pause the video, and write down what you would write in Matlab by defining all those variables. All right? So pause the video when you're ready, turn it back on. Now that you're back, okay, here's what my first few lines of my script file were. Okay. Now maybe if you're a good programmer, you might, and we can do that later, you might put CLC and clear all and close all, stuff like that. But that's not a big deal. But we're in a script file, and we want to define that L, the length of our reservoir, is 1,000 feet. The porosity is 20%. K is 50 millidarcies. CF is 1 times 10 to the minus 6 inverse PSI. The viscosity is 1 centipoise. Alpha is, put our conversion constant, K divided by viscosity, porosity, CF. And keep in mind, I've already defined all four of those things, so it'll be able to calculate alpha. Okay, my initial pressure is 1,000. This is the initial pressure. This is my inlet pressure on the left. That's why I called it PN. Maybe that was a bad name for it, but because it looks like initial pressure. But this is initial. This is a boundary at x is equal to L. Okay, and then this is Q out. Oh, no, sorry, this is at x is equal to 0. This is no flow at x is equal to L. So you may have used different nomenclature, but it should be the same kind of thing. So we defined, we know our reservoir and fluid properties in our boundary conditions. So we defined the length of the reservoir, the porosity, the permeability, the compressibility, and the viscosity. From those things, we could calculate alpha, so I put an equation for alpha, and then I defined my initial condition and my two boundary conditions. That's the first step, okay? We haven't really done much, okay, but that's a program, okay? We could stop it right there, and we could run Matlab, and by running Matlab, it would tell us what L is. It did calculate alpha, so our program did do a calculation. It's probably not what we want, but it's a start, okay? So if I were writing code, if I were writing the code, I would do this by hand like I did. Then I would go into Matlab, and I would type in all those things. I would run it. I would make sure I didn't get any errors. And if I did, then I'd fix them, and then when it ran okay, then I would move on. Because the one thing I hate doing, and everybody should hate doing, is writing an entire code at once and then get 50 errors and trying to fix all 50 errors at once. If you just do this little part, okay, maybe you get a little error. Maybe you used K there, but you called this perm there, and then you got an error, and you're like, oh, well, that was silly, and you fixed it, and then you did that. But if you had 50 of these little errors all at once, then you just drive you up the wall. So we got step 1 done. All right, so that's step 1. Let's do step 2. Step 2 is, well, we'll also need to define some numerical properties. For example, the time step, delta t, the number of grids, capital N, and things like that. So let's do all that. Okay? Pause the video if you need to and scribble some things down and tell me what you would do. And when you're ready, come back. So now that you're back, if you notice, I did this on purpose. I kind of use smaller font and use a light font. And these are the same things I already defined. L, porosity, permeability, compressibility, viscosity, alpha, because that's not new. What is new is I defined N is equal to 4. That's the number of grid blocks. Okay, or maybe N is equal to 11 if I wanted to do like the Excel program. But the nice thing about Matlab is I can change the number of grid blocks like that and rerun the program. Right? So N is equal to 4, N is equal to 11, N is equal to 10,000, whatever you want to do. Okay, I did make one little change here, and before I said the initial pressure was 1,000 psi, but now I want to say that it's 1,000 psi in each of the 4 grid blocks. So I said P is equal to 1,000 times 1s of N comma 1. So that makes it a column vector that's got N is equal to 4 or N is equal to 11 rows, and all of them have a value of 1,000. Okay. Delta X, the size of the grid block, is the length of the reservoir, which I already defined as 1,000 feet, divided by the number of grid blocks, whether it be 4 or 11 or 1,000. dt is 0.01 days or 0.02 days, whatever I want to make it. This is a little tricky. X is going to be the center of my grid blocks. So if I've got all these grid blocks, this is 0, this is L, and I've got N grid blocks. This is delta X, right? That's delta X. So the first point is actually delta X over 2. The last point is L minus delta X over 2. And there are a total of N points. So what I said is I use a linspace command. You might have been able to use colon notation, but X is equal to linspace delta X over 2 to L minus dx over 2 and use an N number of points. And I wanted it to be a column vector, so I transposed it. So that's what I did there. The final time, this is kind of arbitrary, but I said we'll run the simulation until we get to 2 days. Remember, the time step was only 0.01 days, so that seems like it's going to be, what, like 200 time steps? Eta, okay, that was my this thing here. Eta is equal to alpha delta t over delta x squared. All right, and I already put my conversion constant for alpha, so everything should be dimensionless at this point, and that's all I want to do. So now, if I combine step 1 and step 2, I've got a program. And if I were, what I would probably do at this point, and you should actually do this. I think you should do this. I think you should open up Matlab and do step 1 and do step 1, run it, make sure you don't get any errors. Do step 2, run it, make sure you don't get any errors. And you know what? I may have even made a typo here. So if you get a mistake, don't be 100% sure I didn't make a mistake somewhere. But for the most part, it's right. And run it and see that you know things are working okay. You know, you run things from your script file because now we're about to get into the harder stuff. So we're done with step 2. Okay, step 3. We need to compute the matrices and vectors. Okay, so this is the explicit method. So I don't have to solve a system of equations, but you can actually do this explicitly by setting up a matrix. And that's what we're going to do here. This is, it's completely comparable and analogous. You get the same answer, but we're going to do things a little bit different than what we did in Excel. We're going to set up a matrix where this is 1 minus eta times 2. I think that this will be it's going to be something like this. I want to point out that I'm not solving a system of equations because this is still explicit. I'm just doing matrix times vector multiplication, where this is the right-hand side vector plus boundary conditions. So I get a square n by n matrix. This is a n by 1 column vector. And in step 3, what I want to do is I want to create this matrix. And I also want to create a vector, and then I'm going to multiply them together later on. But what's tricky is how you create this tridiagonal matrix. And if you go back and watch the Matlab videos that I did, the review Matlab videos, I actually explain a very simple and efficient way to create a tridiagonal matrix. Heck, in your homework, homework number 1, you had to create a pentadiagonal matrix. So this should seem really easy to you. So what I want to do is a simpler way of thinking about this is remember what our fundamental equation was, which is, it was that, where I is the grid block, and it goes from block number 1 all the way to block number n. So you do this equation for all your blocks, I is equal to 1 to I is equal to n. Okay, I think I just gave away the answer. In fact, I just said you're going to do it for block I is equal to 1 to n is equal to n. So you know what? It's exactly what we do. If I go over here, I do for I is equal to 1 to n. The main diagonal actually, so the way I wanted to do this is the matrix is going to be that one. So that makes it really simple. This is just a simple tridiagonal matrix. So AII is equal to 2 on the main diagonal. AII plus 1 is minus 1. AII minus 1 is negative 1. So that's the main diagonal, the right, and the left. Okay. Now, if you're on the first row or the last row, you have to treat it special, right? So that's where we use our if statements. So if I is equal to 1, okay, I've got boundary conditions and I do things a little bit differently. I gamma 1 is that, and if I is equal to n, then you do something different there. But this is how I create the tridiagonal matrix. It saves me, it's a lot faster if you initialize your variables. So I say a is equal to 0s nn. That's not necessary, but it's going to make it a lot more efficient and faster. So I just make a square matrix of A. B is a right-hand side vector of zeros. And I is the identity matrix. So I just looks like that. Okay, that's the identity, and use the I command, EYE, to create the identity matrix. Okay, so this is what this loop does. This loop creates a matrix called A, which is tridiagonal, with 2's on the main diagonal, -1 on the off diagonals, unless I've got boundary conditions, in which case I think here, and you know, I didn't make it very flexible. I forced this to have a Dirichlet boundary condition there, and I forced this to have a Neumann boundary condition at the bottom. That's why this is that. So if you are ambitious, you can fix my code to where it's got more flexible boundary conditions, so maybe you need more if statements. And the identity matrix is that, and that's all we're going to do there. We're just going to create A and I and B. B is going to be 2p n is what I called it, times eta. So this little loop we created creates A, B, and I. And that's it. That's what this part of the code does. And of course, I didn't delete everything else, but I did use a font that makes it less visible because I wanted to focus on what we've done here. So you can type all this into Matlab, run it, make sure it works. And if it doesn't, then fix it before moving on to step 4. Okay, next step. We want to calculate the reservoir pressure, so the pressure in every grid block, at various times. Continue until the time reaches our final time, or continue while the time is less than the final time. So you're going to use an equation. What we basically want to do is solve P new. It's still the explicit method. I minus eta A times P old plus B. That's what we want to solve right there. And of course, in step 3, we calculated I. We already know what eta is. We calculated our A matrix. We should know what our pressure at the last time step was, or we at least know what our initial pressure was. And we calculated B. So this was step 3. This was step 3. This was step 3. This was step 1. We initialized that. And this was also step 1. That was our initial pressure. Okay? And what do we want to do? We want to do that not just one time step, but we want to continue to do it in a loop. We want to do a bunch of different time steps. So I want to do this. I want to continue to calculate my, so here's my equation. I want to continue to calculate my new pressure. I want to do that a bunch of times, though. I want to do it while the current time is less than T final. And I defined T final, I think it was 2 days in step 1. Okay, time is going to change. The time is going to be initially 0 days, and it's going to be 0.02 days, and 0.04 days, and 0.06 days. It's going to change. So initially, time is 0, and then in each time step, it's going to update. So it's going to be time is equal to whatever time was, so 0 days plus my time step, which was 0.02 days. There's going to be 0.02, then it'll be 0.04, then it'll be 0.06. That'll be a real number, right? A fraction, 0.02, 0.8. I can also use n, little n, that's our time interval. N is equal to 1, then n is equal to 2, then n is equal to 3, n is equal to 4, n is equal to all the way to whatever, 2,000 or something. Notice that in my equation, P is equal to this matrix times my old pressure plus B. My old pressure is going to change every time, right? So it's whatever it was in the last time step. So if I'm on the first time step, P old is going to be P at time 0. If I'm in the 1,000th time step, then I'm going to be using P 999. So what I like to do is I like to save that old pressure. P old is equal to P, and then when I update P and I do this, then it's gonna use the old P old. Okay. There are other ways around that, but I like to do that. And then I made a matrix right here, P plot, and what it's doing is it's saving all of my pressures or a lot of my pressures in a matrix, and that way I can make plots of it later on. Okay, so yeah, there's a lot going on there. It's a small little loop, but there's a lot going on there, right? We're solving the pressure, we're updating time, we're saving it for plots, all that. That's what step 4 is. Okay, so maybe you try to type that into Matlab and see if it runs and make sure things are going okay. Okay, and then, I'm sorry. The last step is I could do some extra things. I could save the pressure at some time intervals. I actually did that in the last time step, so I can make a plot at the end. So what I did is at the end, after my loop, so this is that while loop we just did. This was step number 4 right there that I kind of didn't. But here what you see I've got highlighted is plot x, plot x. X was the center of all my grid blocks. P plot was my plot at different time intervals. Okay, I can go back and look at the Matlab videos. It set GCA font size, changes the font. I put an X label, I put a Y label, I put a legend. I made my background white. Okay, and let me see, that might be it. That's our whole program. Okay, so that was a pretty complicated program, to be honest. If you get that, then you should be set for a lot of the homeworks in the future. Okay, so I would think you should go through all those steps, and I know maybe I didn't explain everything perfectly, but hopefully you understand that, and you go in yourself into Matlab and type it all in and see if you get the right answer. And let me show you my Matlab code. This is my code. This was step 1. That was step 1 where I defined all my variables. Okay, and maybe after the end of doing step 1, I would save it and run it. Step 2, define the numerical properties. This was everything I did in step 2. This is step 3. Look, this is identical or almost identical to what I had in there. So this is exactly the same code. This is step 3. This is create the tridiagonal matrix A. And notice I use a lot of comments because I like to go back and see what I did in the past so I understand it better. This was step 3. That was the for loop. That was what created my A matrix and my identity matrix I and my right-hand side vector V. Then I did my while loop, so I was solving for grid block pressures through time. And then step 5 was to make my plots. So I think this is identical to what I had written over there. So if you understand everything you did in there and you're able to write it yourself into Matlab, then you can run this code. Okay, and no, let me back up. I didn't mean to do that yet. Okay, this is exactly the same problem we did in the Excel problem. So n is equal to 11 grid blocks, dt is 0.002, L is equal to 1,000 feet, K is 50 millidarts. Same problem, so I should get the same results. Let me run it. Okay, and I think I'm plotting it at different times than I did in Excel, but you get exactly the same type of response. This is the pressure, goes over there. I'm going to use, if I had used a bigger time step though, it becomes unstable, just like it did for the explicit method. Now if I want more accuracy, I can use more grid blocks, but I get to use a smaller time step. So let me do something like that. Let's see if okay, you see what I did there? I used really small time steps, and I used 100 grid blocks, and now I get a really accurate solution because I got more points. And now it's more clear that it's coming to the right solution. So the boundary condition, remember, was 2,000 psi. The boundary condition over here was no flux, so the derivative dp dx should be 0. It should be flat, right? That's exactly what I get. Okay, so more grid blocks means more accuracy. It also means it's going to run slower. Okay, and it also means if I use more grid blocks, I got to make my delta t really small to make sure that my eta, and I can check what my eta is, 0.4194. So I'm right on the fringe. If I used any more grid blocks or any bigger time steps, then it would probably. Oop, I didn't mean to do that. But this is my code, and it works pretty well. Okay, this is with 100 grid blocks, more accuracy. I could do 4 grid blocks, kind of like what we do with our hand problems for homeworks. And okay, so same qualitative behavior, but obviously not as accurate. So we like to have more grid blocks because it gives us more accuracy, but that means a lot longer simulations, a lot more computations. It also means some instability if I don't use a small enough time step. So I think that's all I got. That's the end of our video lecture on the explicit and implicit method for solving the heat equation using both Excel and Matlab. Excel was very good for kind of visually understanding what's going on. Matlab is much more flexible because, as I showed here, I can go in and change the number of grid blocks like that and able to get different solutions. In Excel, that wouldn't have been very easy at all. In fact, almost impossible. But thank you.